First off, a big thanks to our two colleagues earlier for helping upgrade our system with AI capabilities. Our NIO assistant is super smart. I'm Shaoqing Ren from NIO's Autonomous Driving R&D team. Great to be here for the second year at NIO IN. After last year's talk, I got a lot of feedback from old friends. They said the tech story was cool, the tech itself was solid, but I wasn't speaking much in everyday language. So this year, I'll try to make things easier for everyone to understand. Last year at NIO IN, we introduced NIO's full-scope Enhanced Pilot Assist (NOP+) for the first time. What makes it different from others is how we share routes, creating a network of verified roads. These routes are all validated by our collective intelligence system, helping us roll out in urban areas. Since last September, our Enhanced Pilot Assist has covered a huge amount of ground. Literally. Nationwide, we've now mapped out 3.89 million kilometers of drivable routes. NIO users have already logged over 1.1 billion kilometers with our Pilot Assist. As you can see, NIO drivers are really into road trips and love being behind the wheel. All those miles covered are thanks to our underlying collective intelligence system, which has been a huge help over the past year. Our car cloud computing power reached an impressive 287,000 POPs, sourced from all our cars and cloud servers. With this computing power, we've managed to validate 420 million kilometers of roads for urban, highway, and active assist in just the last year each month. We identify about 220 million samples to help us spot issues, fix problems, and iterate. All of this makes our driving and safety features evolve faster than ever. We're really entering a new era for autonomous driving. Last year, we talked a lot about expanding into urban areas. This year, though, you've probably been hearing more buzz around end-to-end architectures. If you're in the tech scene, you've likely been asked, did your system integrate end-to-end yet? And which type are you using? Well, we've already implemented it in our version 265. Our mindset has always been that any tech upgrade needs to actually improve safety, right? After all, reducing accidents has always been our top priority. That's why, with version 265, we were the first in the industry to introduce an AEB, automatic emergency braking, feature based on end-to-end architecture, and it's already available in many users' cars. When it comes to active safety, the biggest challenge is covering real-world scenarios while minimizing false alarms. What you're seeing here are standard regulatory test scenarios. Basic parallel or vertical situations, like driving toward the car in front of you and making sure you can stop in time. The new standards, NCAP 2023 and CNCAP have even introduced some cornering scenarios. But when we compare those regulatory test scenarios to real-world situations, it's clear they are still far simpler. Based on our data, regulatory scenarios only cover about 10% of real-world driving situations. The real world is far more complex, and that's what we're working to solve. Making sure you're safe in those unpredictable, everyday driving conditions. Tackling this complexity requires new technology. And that's where end-to-end active safety comes in. Traditional systems handle simple, linear situations, but with our end-to-end solution, whether a cyclist cuts in from any angle at an intersection, our car can stop safely if needed. This represents a huge technological upgrade, and is also a massive data challenge. We've gathered data from 2.1 billion kilometers of real-world driving scenarios, with over 10,000 accidents, and validated these across 400 million kilometers of testing with our collective intelligence system. All of this data is driving the success of our end-to-end safety system, which has already greatly enhanced safety for our users. So, we just saw a pretty immersive video. But now let's dive into the real data. Our end-to-end AEB system covers real-world scenarios 6.7 times more effectively than the standard regulatory AEB systems. We just talked about our end-to-end AEB system. With this end-to-end architecture, we're upgrading our active safety system to NIO Intelligent Safety Assist 2.0. This includes the end-to-end AEB system and the upcoming end-to-end GOA, General Object Avoidance. These upgrades significantly increase the range of scenarios our system can handle. In the past, we relied only on regulatory standard scenarios. But now we can respond to real-world situations too, helping solve the complex problems of everyday driving. Beyond just covering more scenarios, we've also improved the system's maximum emergency braking speed. Our end-to-end AEB is already live, and the end-to-end GOA will soon follow. Tackling unregulated objects, we hope that NIO Intelligent Safety Assist 2.0 will offer all-encompassing, full-speed intelligent safety, making your driving experience even safer. So far, we've mainly talked about features, but behind these features is what we've been calling the end-to-end approach. It's really all about upgrading the algorithms. Why has traditional active safety been so challenging? Well, it needs to solve real-world problems while also being extremely accurate. Like only making one mistake every 100,000 kilometers or more. Otherwise, drivers would find it incredibly annoying. In the past, we used perception algorithms followed by manual rule writing for specific scenarios. This works fine for regulatory scenarios. But when it comes to the countless real-world situations, it's just not practical to have engineers writing rules for every possible case. That's why we're upgrading to an end-to-end system. Instead of manually coding rules, we now rely on data-driven models. The model collects data, trains itself, and solves problems on its own. With this end-to-end algorithm, performance has skyrocketed. To sum it up, there are two key benefits. First, we've moved from manually written rules to model-driven, data-powered iterations, making the most of the data we collect. Second, traditional hand coding often leads to information loss. But our model-based approach automatically extracts information, reducing loss and making better use of the data. But there's one more question we want to address. Everyone's talking about end-to-end. But is that enough? When people drive or do other tasks, do they use abilities beyond what end-to-end systems can do? And can our car's intelligent driving system learn those abilities to drive even better? Alright, let's do a little experiment together. A thought experiment. Please sit comfortably and close your eyes. Like our NOMI assistant
Lights
would
out,
say, please close your eyes. Alright, now imagine a tree. It's been growing for 10 years. Its branches are full and leaves abundant. Now it's summer, an afternoon in the middle of the season. The sun is shining on the tree, and a soft breeze rustles the leaves. Time passes, and in just 3 short months, summer turns into autumn. The tree's leaves turn a vibrant gold. Another 3 months go by, and autumn fades into winter. Snow falls, covering the tree in a blanket of white. Alright, let's open our eyes now. We're moving from that imagined world back into the real world. Back to where we are right now. What we just experienced was a journey through the mind, an exploration of the brain. You might not have realized it, but what we just did is something every AI researcher marvels at. The incredible power of the human brain. What you see here is a representation of the human brain. from the eyes on the left, through the blue area, which is the hypothalamus, and up to the yellow part, which is the cerebral cortex. This forms what's called an internal model of the brain. And what's the point of this? Well, like we just experienced, when you close your eyes, even though you didn't actually see a tree in front of you, your mind created a vivid image of one. That's the first point. The second point is when you dream at night. You see all kinds of scenes, things you've encountered before, or maybe even things from many years ago. Last night, while I was preparing this presentation, I was lying in bed, and in my mind, I could already visualize what the first slide would look like, then the second, and so on. What I imagined in my head turned out to be exactly what you're seeing projected on the screen today. I'm sure many of you have had this experience before. That's the second example. The third example is when you're walking down a familiar street in your neighborhood. Maybe you're on a phone call, or eating something, not really paying attention to the road, but you instinctively know what's around you, because your brain has already built a clear image of the entire path. Your brain has already mapped out the full shape and layout of that road in your mind. So, to sum up our mental journey, the human brain has two key abilities. First, it has spatial understanding, which we can also call imaginative reconstruction. When I asked you to imagine a tree, you didn't see it in reality, but your mind instantly conjured one up. That's the first ability. The second is our sense of time, or imaginative progression. When I asked you to picture the tree changing from summer to autumn, then from autumn to winter, your mind seamlessly filled in those 6 months in just 2 seconds, giving you a clear sense of time passing. These two abilities together form what we call spatio-temporal cognition. It's our understanding of the changes and possibilities in the three-dimensional space and one-dimensional time we live in. This ability is crucial for humans living on Earth, and it's just as essential for intelligent systems, like self-driving cars or robots. This ability allows an intelligent system to create an abstract world in its mind, one that follows the same rules we do, especially the laws of physics. This is what we refer to as a world model. We believe that for an intelligent system to be truly smart, like all of you here, it needs spatial cognition to reconstruct its surroundings, and temporal cognition to predict changes over time. So, back to the question, is end-to-end enough? We believe because an end-to-end model doesn't necessarily have these two core abilities we've been talking about. We aim to build a model that, like the human brain, has an internal model of the world. A model that can imagine space and predict changes over time. Last year at NIO IN, we talked about this concept of a world model. At that time, it wasn't quite ready, but after another year of development, we're excited to share it with you and prepare it for mass production. We call this the NIO World Model, or NWM. Moving forward, when you see NWM, you'll know it refers to a system that learns spatial cognition, imagines reconstructions, and predicts time-based changes, just like a human. Let's dive into the first part of this, learning spatial cognition and imagining reconstructions. We believe that being able to imagine and reconstruct is the highest expression of spatial understanding. Remember the tree we asked you to imagine earlier? Well, here's a real picture of a tree. Now, think back to what you imagined. Some of you might have thought of something like this, but maybe with fewer details, not quite as vivid. Others might have imagined something more detailed, Like this sketch, it's more intricate, closer to a realistic rendering, which shows a deeper understanding of space. Some of you may have pictured something even more lifelike. A tree in full motion, with leaves swaying in the breeze. This level of imagination shows not only that you're familiar with trees, but also that you have a strong capacity for spatial cognition. A moving tree like that signifies a high level of familiarity with trees, a strong imaginative ability, and deep spatial cognition. It also shows something else. We're all incredibly intelligent systems. We want our model to be able to do the same thing. But how do we achieve that? We've simplified the output of the model. We want the model to be able to take in a video and also output a video. For example, just like we showed earlier, input a picture of a tree and output a moving, realistic tree. Input a real-world driving video and it will output a video in a parallel, imagined world. This is the core capability of our model. In fact, the whole evolution of autonomous driving technology has been about improving spatial understanding. What you're seeing here is an early, raw video from around 5 years ago. Back then, driving algorithms would transform videos into something basic. You'd see boxes around vehicles and lane markings on the road. Sure, it extracted some information, but not much. Then, algorithms evolved. You've probably heard of the BEV, bird's eye view, method. It extracts way more information than 5 years ago. But it still misses things, like the edge of the road or unusual objects. So the algorithms improved further, reaching what we call OCC. OCC goes from a 2D representation to a 3D one. Kind of like those pixelated games we played as kids. The information becomes much richer. But when you compare OCC to the real world, it still lacks details. For example, the texture of the road or whether it's snowing. It doesn't express those. Small objects, like a raised tollgate bar, are missing too. While OCC is impressive, it's not quite there yet. We want to take it to the next level, reconstructing the world to be closer to reality. In the bottom right of this video, you'll see the result from our NWM model. It's not a real video, but rather something imagined by the model. A parallel world created from the information it extracted. This is the next step in the evolution of spatial understanding. Autonomous driving's history is, in many ways, the story of how spatial understanding has evolved through algorithms. Now, having the ability to reconstruct means the model has a deeper understanding of the real world. Just like when you all imagined different trees earlier. Some pictured a banyan tree, others a pine, or maybe a willow. The real world is full of different conditions. Snowy days, rainy days, and more. We want the model to be able to do the same thing. To learn and generate these scenarios. Here, for example, is a snowy day. A snowy day. And now, a night scene. Daytime, and every other scenario. Cities, highways, small roads. All of these videos are generated by the model. They aren't real. The first few seconds are real. But the rest is entirely created by the model. So what the model does is watch tons of videos, learns from them, and understands the infinite possibilities of the real world. In its mind, it can imagine and reconstruct these scenarios. Just like how you imagined the tree earlier. This gives it the foundation to handle and drive in all kinds of environments. Earlier, we talked a lot about imagining and reconstructing videos. From a technical standpoint, this approach has some key benefits. First, it's a self-supervised process, meaning we don't need to label data, which makes it much more efficient. Normally, training models requires a lot of effort, data, and computing power, but this method allows us to scale much more easily to millions, even billions of data points. Second, because it's generating videos, the tasks are more complex and contain richer information, which helps the model learn faster. Okay, so the first ability we discussed is how the model can now imagine and reconstruct things. The second ability is even more exciting. It can predict changes over time, just like when you imagined the tree earlier. Now imagine how it changes from fall to winter. We believe this ability to visualize change over time is key to understanding not only time but also space. The richness and realism of these imagined changes reflect how deeply the model understands the world. Last year, a video generating model called SAR became an overnight sensation. Why? Let's break it down. First, the videos it generated looked incredibly real. Second, it could create all kinds of scenarios. And third, it could generate longer videos than most models before it. Essentially, it was learning the rules of how the world works. Physics, space, and time. It wasn't perfect, but it marked a big step forward for AI. Now, we hope our model can go beyond just imagining still images. It needs to continue imagining over time, generating videos that predict future events. We're teaching the model to keep thinking as it moves forward in time. Here's a video generated by our model that's over 2 minutes long. That's already better than most other video generating software out there. In a driving scenario, even at a slow 30 km per hour, about 18 miles per hour, you're still covering more than a kilometer, 0.6 miles, in 2 minutes. This means the model needs to create complex backgrounds and a wide variety of changes, like traffic jams, while also following physical rules. Whether it's static or dynamic, the model's understanding of space and time deepens with these long videos. But this isn't easy. The first challenge is making sure its imagined reconstructions are accurate. This depends on how good the model is, but also on how much real and diverse data we give it. We've fed the model millions of clips to learn from. Think about it. If you see something familiar every day, like a tree, you can picture it very clearly. But if you only see something once every year or two, it's harder to imagine. The same goes for the model. It needs tons of data to get better at imagining. Second, since the video is long, we need it to stay consistent over time. That's why we developed a new spatio-temporal encoding method to improve the model's continuity. There are other engineering challenges too, but those are mostly related to memory and data training. Overall, our model is currently one of the best at generating videos in the field of autonomous driving. Now, aside from letting the model imagine freely, we also want it to respond to commands. For example, in self-driving situations, we can tell the model to turn left or right, or switch between lanes. On a more detailed level, it can adjust the steering wheel by any angle or control the speed. With these instructions, we can guide the model's imagination and have it follow our commands while predicting how a driving scenario might unfold. In this example, we're following a red truck. The video starts with a real-world clip, but then the model takes over, imagining various possible outcomes. The truck is moving slowly. So we want to see what would happen if we changed lanes to overtake it. Either from the left or the right. Or maybe we just stay behind it. What are the different possibilities? The video shows only a small portion of the many scenarios the model can imagine. It covers a wide range of driving situations and possibilities. This shows how deeply the model understands time and space. It can predict thousands of possible worlds and find the best driving decision. Whether it's the safest, the most comfortable, or the fastest. Earlier this week, when we were discussing this with the team, it reminded us of a popular concept from a couple of years ago. Time travel. There was a viral TV show called *Reset*, where the main character goes back to a parallel world to prevent a bus explosion, trying again and again to find a solution and escape. Our world model can do something similar. Imagine you're driving, and there's a minor accident, like a fender bender. We can have the model time travel back 3 seconds before the accident to explore different outcomes. Without being explicitly taught, the model can figure out that in one scenario, it should hit the brakes, and in another, it should turn the steering wheel. These kinds of reactive driving skills are still rare even in current mass-produced autonomous driving systems. But our model learns this just by watching videos. It naturally understands when to brake or swerve. The model can essentially travel into a safer, alternative world. These two abilities, imagining and reconstructing space, and predicting changes over time, combine to give the model a deep understanding of both space and time. Together, they form the core of our world model's brain. Ultimately, though, this is still a self-driving model. So its goal is to actually drive. That's why we want the model to output a planned driving trajectory, essentially showing us how it would drive the car. With the ability to plan a trajectory, the model can generate an imagined world and figure out how the car should drive in that scenario. In the video, the green dots show the car's driving path. And in the top right corner, you can see the model's predicted steering angles and speed. Based on its imagined world, the model easily learns how to drive. So, here's how it works. Our NIO World Model generates 216 possible driving paths every 0.1 seconds within its imagined space. It evaluates each trajectory to pick the best one. Then, based on real-time input from the environment, it updates its internal spatio-temporal model and predicts the next set of 216 possibilities. This cycle of imagination, prediction, and trajectory planning forms the core capability of our NIO World Model. Of course, the model's capabilities go beyond this, and we'll dive into more details in the future. To sum it up, compared to conventional end-to-end models, our new world model has 3 main advantages. 1. Enhanced spatial understanding. Using a deep layered model to reconstruct sensor inputs allows for more generalized information extraction and deeper spatial comprehension. 2. Superior temporal reasoning. Through an autoregressive approach, the model automatically builds and understands environmental contexts, giving it stronger predictive abilities over time. 3. Massive data handling. Leveraging self-supervised learning. Our model doesn't require manually labeled data, enabling it to learn faster and handle millions of data points efficiently. In essence, the NIO Intelligent World Model, NWM, is a multifaceted generative model, designed to enhance our learning capabilities by imagining parallel worlds for driving. With this new model, its capabilities are incredibly robust, especially since it's a world model. It requires vast amounts of data. In large-scale AI applications, obtaining real-world data isn't always easy, whether it's for our model or for robotics. We believe that intelligent driving has the most mature data loop among AI applications and is the most likely to see large-scale, safe implementations. In our system, collective intelligence and deep layered simulation are our secret weapons at the data level. They meet the extensive data needs of our world model. Last year, we introduced a lot about collective intelligence. In scenarios where we have a large fleet of mass-produced vehicles, we can distribute different versions of the world model to tens of thousands of cars. These cars can compare their driving states with human drivers and with more stable, mature autonomous driving solutions. This helps identify what scenarios the model handles well and which ones it struggles with. Using government samples to iterate and improve. For special scenarios, we can transform this data into post-validation simulation data to better train the model. Now, let's take a look at what our advanced simulation is doing. We're using real videos to reconstruct entire worlds. We call this the simulation model. It can separate foreground from background, switch to any angle, and analyze detailed information like depth. Next up is the fermentation process. After classifying all the objects and people in the data, the model rebuilds the three-dimensional world. This means that, when it returns, the car doesn't just follow its original path. It can choose any trajectory, even fly, to reconstruct the world. This allows the car to drive along any path it wants, while dynamically editing moving objects as needed. Essentially, this gives us the ability to take real-world videos and reconstruct a virtual, editable world. This is the result of our NIO simulation, NCM. On the left side of the screen, you'll see markers showing the simulation results. These simulated outcomes provide us with more ways to manipulate the real world. Earlier, we talked about our world model. It uses original video input to imagine possible outcomes. For example, it can envision scenarios like turning left or right. But in the real world, there's only one actual outcome. The world model compares this real-world result with its imagined outcomes to learn and validate its predictions. Even though it can imagine many scenarios, it can only learn from the single real outcome. With the NCM simulation, things change. Our world model can now imagine millions of possibilities, and the simulation can generate just as many based on those predictions. By comparing all these variations, we can validate and train the model across countless simulated worlds, making its imagined scenarios more accurate and its driving outputs better. So, what you see here is a real example. Our visual model has imagined various possibilities, and in the simulation world, we can observe its predictions. By comparing results in this parallel universe, we can enhance our model's learning. In summary, our NIO World Model is a multifaceted autoregressive generative model, which includes our end-to-end active safety model and other mechanisms. Together, these constitute our second-generation algorithm architecture, representing a groundbreaking shift from last year's framework. Based on this new architecture, we've focused our product functionalities into two key offerings: Point-to-Point Navigation Assist 2.0 and Intelligent Safety Assist 2.0. These features will continuously provide users with a more effortless and safer driving experience. Thanks to the new architecture, our Point-to-Point Navigation Assist will roll out in the second half of the year. The Intelligent Safety Assist 2.0, which includes AEB, is already available in the 265 model, with more features like GOA coming soon. Many of the models we mentioned are cutting edge, especially the generative and world models. As AI technology advances rapidly, these models demand higher computing power. Our Adam platform is well equipped with sufficient computational resources, ensuring we can maintain a leading edge in architecture and algorithms, delivering an exceptional experience for our users. Additionally, our newly launched Shenji 99031 chip embodies a wealth of collective knowledge and effort from our team. It's specifically designed for our world model, and we believe it will exceed expectations. All these technological advancements and product upgrades aim to achieve our core mission: reducing driver workload and accidents, making driving easier and safer for everyone. Thank you all for your attention to our latest developments in intelligent driving. Now, let's welcome Bin Ji to the stage.